A matrix, it's a mathematical construct. Maybe I have to write this one. A mathematical construct that carries numbers in an array of numbers that can look like this: 2, 1, 3, minus 1. So this is a matrix. It's a 2 by 2 matrix. Okay, it's a square matrix. It's a square because the number of rows is equal to the number of columns. Here we have another matrix which can be called like a 2, 0, 0, 3. This matrix it's a square again. So these are all mathematical constructs. This is a square matrix, but it's also diagonal matrix. Okay, we call this diagonal because only the diagonal terms are present. The non-diagonal terms, they are all 0. Then here we can have another matrix which is C is equal to 1, 0, 0, 0, 1, 0, 0, 0, 1. This is again square matrix. It is diagonal matrix, okay? But because it's diagonal, because all the off diagonal terms, they are all 0. Now the difference between this and this is that this is also called an identity matrix. Identity matrix is when CII is equal to 1. CII equal to 1, this means that when the index of these numbers are both equal, then they are 1. And for example, here, we can denote that A11 is equal to 1. A11 is the first row, first column. So here we get a 2, okay? And then we have A21. A21, this is the second row, and the first column. This is equal to 3, okay? Then we can have A12. In this case, it's going to be equal to 1. So these matrices that we have shown here, they are all square matrices, but we can also provide one which is D is equal to 1 minus 1, 7, 3 minus 4, 5. This is a matrix which is 2 by 3. It has 2 rows and 3 columns. So for example here, D 1, 3, this is the first row, third column, this is equal to 7, okay? So these are the matrices as mathematical constructs where we have numbers organized in a specific array. Now, we can also go over a couple of short definitions of matrices, but for this one, we can start sharing the screen. So, as we said that the matrix it was a rectangular array of numbers, and here we have the matrix 1, 2, 3, 4, 5, 6. In this matrix, we notice that the 3 is, for example, element of the first row, third column, and 6 is second row, third column. The second matrix, it's a vector which is 3 rows, 1 column. And the last matrix, it has m rows and n columns. This is how we denote those. Second. Okay, so here we denote that any entry in the ith row and jth column, we denote it as aij. And then we can also have vectors as shown here, vector A and vector B, which are simplified versions of the matrices. Then here we define.
Professor.
Yes.
We are not seeing what you're presenting. We're seeing only the table.
If you've been at my screen, you know, maybe you should have an option where you can select to see the board, to see the camera, or my screen. Can we ask also other students? Do you see my screen?
Yes, we can see the screen.
So probably in the list of participants in this online class, you can see my name twice, and my name is twice because you can have two sources of information. One is the camera, when I am on the board, and the other one is the monitor. Is it fixed now?
Yes, it is.
Okay, thanks. Okay, so we defined on the board what the diagonal matrix was. And a diagonal matrix is a square matrix with all entries which are not on the diagram equal to 0. Then we can also determine that two matrices are equal only when they are the same size and all the entries, all the numbers are equal to each other. So two matrices of not that has different dimensions, they cannot be considered to be equal at all. Then okay. So now diagonal terms in a matrix, as are shown here, is A11, A22, and A33. And these are, we can talk about a matrix being here, okay? Maybe I can mention this one in the next slide. Now, matrices, we can partition them as shown here, and with the partitioning, it can be very beneficial because sometimes we may have large matrices and we want to do complex computations. And when we have complex computations, the number of calculations that are needed to be conducted, they can be huge, okay? And for this reason, it might be better to partition the large matrix into smaller pieces and then operating with those. And these matrices, we can divide them by drawing horizontal line and vertical lines as shown here in this slide. So this is beneficial, especially when we have a lot of calculation to conduct. Because operating with matrices is very computationally expensive, okay? And with computation expensive, we need a lot of computational time, running a computer for hours. Now, we can also define zero matrices, which are matrices which are full of zeros. We can define, I think we talked about the identity matrices. Identity matrix, they were diagonal matrices where all the entries, they were equal to 1. Here, we have an example of 2 by 2 matrix and 3 by 3 identity matrix. Now, we can simply define the arithmetics of matrices, and the simplest one is addition and subtraction. And we can see that addition and subtraction, A plus B, it is equal to Aij plus Bij at the same time. Then we have matrices of different sizes that cannot be added or subtracted. Here, we can see it again that Aij plus Bij is the addition of each element. This is how we add or subtract matrices. Then we can also define the scalar multiplication of a matrix with a constant number. So we can have a simple number. We just multiply the whole matrix, and all entries in the matrix would be multiplied 1 by 1. Now, regarding matrix arithmetics, now in this part, I think we can. So let me see. So I guess the last two matrices that were written on the board, they were actually, let's keep this D here. Let's keep this matrix D, and let's write down the matrix B, which was on the slides, and B in this case, it was equal to 8, 0 minus 9, 8, 0 minus 9, and 10. And the other one is at 11, minus 6, 6, 7. Okay, so this is the B, and then let's add the D a little more, because at this stage, B and D, we cannot add them. So for example, if this is D, B, if it is 2 by 4, okay, plus D, which is 2 by 3, So if we add them like this addition, it is simply not defined, okay? So we don't answer this question, because this is not defined at all, okay? But what we can do is that we can add a couple of more numbers. We can add here -1, -1. Now this is equal to t, and now these two entries, they can be added. But the question is, how can we add these two matrices? We have the following: matrix B plus matrix D. This is equal to Bij plus Dij, and I is a number. What is I? I is a number which changes from 1 to 2, okay? And J, it's a number which changes from 1 to 4, because we have 2 rows and we have 4 columns. So once we scan all of the possible values of these, that means that we can add the matrices. For example, if you want to add them, B plus D, we simply report that, for example, to find this element 1, 1, we add B11 plus D11. So we just add these two numbers. Okay, so we have A plus 1, we get here 9. The next element is 0 minus 1, we get -1. Then we have this element plus this one, it's -2. And the rest is 9. Then we have 14 -10. Okay, -10 because we have this entry and this entry. Then we get here 11, and then we have 6. Okay, so this is how we define the addition of B and D. Now, this was just about the addition, but now we're going to talk also about other operations such as multiplication of the matrices. And let's continue. So this was, we can also define a linear combination of matrices. So if you have few matrices and few constant numbers, scalar numbers, C1 times A1 plus C2 times A2 plus Cn times An, this can be defined as a linear combination of all the matrices. But these matrices, they have to be of the same size, otherwise we cannot add them. Now, we can also define the multiplication of a row with a column. And now imagine for a moment that we want to multiply the row here with the column. You need to take a note here, because this is very important, as we're going to cover very soon the inner product, or the magnitude of a vector. Now, just notice here that the only possible multiplication is when the number of columns of A is equal to the number of rows of B. So here we have AN and BN. Okay. Then here we have the definition of the multiplication between any two matrices, and we can. And I think we can stop here for a moment. We have a look at this slide, and we are going to pass to the board for a second. So what is written here is that, first of all, if you want to multiply A and B, A can be a matrix which is n by n, and this will be multiplied with a matrix which is n by k. And for this multiplication to be defined, the first thing we have to notice, or to be careful about, is to check whether these dimensions match. Okay, so this should have n columns, this should have n rows. So if these two are equal, so the first thing that we look for is this. If this is true, then we write that the answer is n by k. It's another matrix C, which has m rows and k columns. And the multiplication here, every element of C, it is defined as Cik. Cik is equal to Aij times Bjk. Okay. Now, this is how we multiply them. Now, the thing is that whenever you see in a notation like this, j is twice, okay? What this really is, this is a summation. This is a summation, and the summation this can be written like this. This is the summation when j goes from 1 to some number, and this is a ij times b jk. I think it's best if we provide an example here. Let's have here for a moment. A is 1, 2, 3, 5. 1, 2, 3, 5. I'm just getting this from the slide. Minus 4, minus 1. Minus 4, minus 1, 0, 6. This is A, and the B, 8 minus 2, 0 minus 1. 8 minus 2, 0 minus 1, 5 minus 1. 1 minus 7. Okay, so here we have A and B, and the first question is, can we multiply A and B? Okay, so is this multiplication defined? Can I have an answer from you? Can we multiply A times B? First of all, what is the dimension of A? Dimension of A is what do you say? Okay, so this is 2 by 4, this is 4 by 3, which means that we can multiply those because this index and this index they are equal. So that's good. We can multiply those. And then the question is the following. If we can multiply those, what is going to be the dimension of C? Let's write the same expression here, copying from here. So we have A 2 by 4 times B 4 by 3. This means that we're going to have a matrix which is 2 by 3. Okay? And let's write here the matrix C is going to be equal to 2 rows, 3 columns. Let's find, for example, what is C12? So let's keep this element. Let's try to identify what is this. 2 rows, 3 columns. We expect such a matrix. Let's find this one. What is C12? This is equal to, let's read it from here. So it looks like I and K. I is 1, okay? K is equal to 2. So we're reading from here, and then this expression, and what is J? J is a number which goes from 1 to 4 in this case, okay? Because J is the second index of element A, and the second index is always the number of columns. So then we can rewrite this expression here, which will be C12 is equal to A, this is Aij, this is A11, B12, plus A12, because this is what J is equal to 1, okay? This is the first term of the summation. This is A I1 B1K plus A I2 B2K plus A I3 B3K. We have one last term, okay? So here we have A12 B22. This was the second J plus A. And notice that the first indices, they never change, okay? So the changing indices here Okay, so this is what I want to say is that any multiplication that looks like this, in fact, what we are doing, we are summing over the j. And this is how we do this multiplication. Now, let's just substitute all the relevant numbers. Here we have a1 1 times b1 2. In principle, we can also say this. C12 is equal to the multiplication of the first row of A, okay, with the second column of B. So this is what you can notice here. For example, A's, in every multiplication we have A11, A12, A13, A14. Here they are, A11, A12, A13, A14. And the respective B's, it's always the same index, so they always denote the second column. You see here, B12 is this. B22 is this. B32 is third row, second column. Second column, it always stays the same. So you are going to track down these four numbers with these four numbers, okay? And then as an answer, we get the following. 1 times 5, okay? Because we are multiplying this with this. Plus 3 times minus 1, plus 3 times minus 1, plus minus 4 times 1, plus 0 times minus 7. This is all equal to, we get here 5 minus 3 minus 4. This is equal to minus 3 minus 4. What is that? Minus 2. Okay, so this is how we multiply these matrices. Now, let's get this element here. What is this? This is C23, okay? C23, how do we get this element? Because it's second row, third column. This is going to be equal to the second row of A, okay? It's this row here, multiplied with the third column of B. Third column of B is right here. Then we move ahead. We say that we have 2 times 3, 2 times 3, plus 5 times 6, plus minus 1 times 4, plus 6 times 0. So finally, we get here 6 plus 30, 36 minus 4, 32. Okay, so this is how we can calculate one by one all the relevant numbers when we multiply any two matrices. Okay, so this is the matrix multiplication. And then we can move ahead again.
Professor,
Yes.
sorry to interrupt you, but I think I am finding this really hard because we haven't learned the basics of mathematics yet.
Okay.
Yes, me too. We didn't do the first hour, so
Which was our?
we didn't get those. The first
When?
lesson of linear algebra.
When today?
We were supposed to do the first lesson yesterday, but the teacher wasn't available.
Okay, but that's fine, but this is not prerequisite. It's not, this is a new piece of material. Okay, we're just multiplying, so we can come back to here. We're not sharing the now. Okay. So what are you missing here? What part you did not understand? You should not be missing much, okay? Because I'm explaining this for the first time. It's not
I
something that.
think the idea of I and J is a little bit unclear to me. I don't know about the others.
Okay, then let me ask you this. Multiply wait a second. So all I'm asking from you is multiply element-wise multiplication of the second row here with the third column here. What are you going to get? So notice.
Okay.
Let's
With
see
the third column,
Yes.
the second row and the third column.
Yes.
So we're getting a 6, then a 30, then a minus 4, and then a 0.
Exactly. Yeah, that's what I was trying to write here. Okay. So
Okay.
you get 36 minus 4, you get 32. Okay? And then let's see how do we get the first element here. How do we get this? First of all, is it clear why this C should have dimension of 2 by 3? 2 rows, 3 columns. We should be able to read this here because first of all, this will be equal, and secondly, these dimensions, they appear here.
Okay, that is clear.
Okay, thanks for confirming this. But let's try to identify also this one. How do we find this number?
This would be C1, 3.
Exactly. This is C13, which means that in the resulting matrix, we pick up the first row, third column. We don't know this. Okay? How do we find this? This should be equal to the first row of A. Okay, because this means that we pick first row of A. How can I write this? I know how to write this one, but let me write this one A1. Okay? Times, in fact, the first row is like this. You pick up first row, you multiply this one with the third column of B. Okay?
Okay, now it is more clear.
Sorry?
Now it is more clear. I can understand it now.
It's better. Okay, that's good. Thanks for confirming again. So this C13, we pick up the first row. Let's pick up the first row here. Let's take this out for a moment. So we need the first row of A, this is the first row of A. We multiply this one with the third column of B. Yeah, we multiply the same one here. So we just do pairs, element-wise, pairing and multiplication. Again, that makes this what? Here, so can you help me here? How can we do the multiplication of these two?
Okay, we should write 3. So 1 times 3.
Yes.
3 times 6.
Yes.
18. Minus 4 times 4. Minus 16. And then 0 times 0, 0.
Okay. So this is, so we just pair them up as a pair, right? 3 plus 18 minus 16. What is this? 5, right? Double check this one, maybe there's something wrong. So this is 5, okay? Yeah, so this is how we do this matrix multiplication, okay? Now, let me ask you this. We can find more actually. So let's do this, let's try to find this element. What is this? We multiply the first row with the first column. So this is 8, 8 minus 6, it's 2, 2. Did you get the same number here? Or who can find this number here? C21.
1 times 5
Okay.
plus 3 times minus 1.
But wait a second. C21, let's check for a moment. C21, this is the second row of A. Okay. Times the first row of B.
2 times 1, 2 times 5.
So, sorry, 2 times 5, but this is 2, 1. I think we have to multiply, let me do this in blue.
2 times 8. 2
Yeah, 2
times
times
8.
8. Okay, so let's follow these in blue, right? So not this, but it's more like follow this row in blue and this column in blue. I think I'm correct.
Yes.
Yes, okay. That's 2 times 8.
Plus 5 times minus 2.
Yes.
Plus minus 1 times 0. Plus 6 times minus 1.
Okay, that's correct. So we get here 16 minus 10 minus 6, we get a 0. So here we get 0. We need one final element, and the one final element is going to be this second row in blue multiply with this discontinuous line in blue, which makes it 2 times 5, it's 10, minus 5 is 5, minus 1 is 4, 4 minus 42, it's minus 38. Okay? But I thank you for your for interrupting me so that we can go a little more slower on this one. So are we good here?
Yes, thank you, Professor.
Okay, sure. And now let me ask you this. What is B times A? Can you find B times A? So we have matrix A, we have matrix B, but let's calculate now B times A. What is this equal to? First of all, B has a dimension of 4 by 3, right? What is the dimension of A? It's 2 by 4. Because we have 2 rows and 4 columns. And B, it has 4 rows and 3 columns. So if you multiply these, what are we going to get? The first thing that we ask is the following. Are these dimensions...
Yeah, it is 4 by 4.
We cannot multiply
4
them.
times 4.
The multiplication
It's not
it is a
possible.
possibility to be 4 by 4, okay? But the thing is that this multiplication is not defined because these two are not equal. You see? Because if you put here the A, you have 3 rows here. If you have to multiply the columns of A, you don't have enough elements. So we can say that not defined. We can simply not multiply them, okay? Is it clear?
Yes.
Okay. Okay, so this was that's something about related to the multiplication of these matrices. And then what we can cover another example. I'm just looking through the okay, so after this small extra coverage, we can go back to the slide. So this was the multiplication of these two matrices. Now here we have two matrices C and D. We can do this as an exercise to check what is C times D and D times C. Okay. Will the multiplication of these matrices be defined? What do you think?
Yes.
Yes, because they are both 3 by 3, right? So things are good. So we don't have any problem. Now, this is something that we discussed on the board regarding how to multiply the rows of A with the columns of B. And here, this is again matrix multiplication. So I think we can also skip this one because just this is again what we mentioned before a while, where we said that we just pick one row of A, we multiply with one specific column of B. This is how we move on. And here we have something interesting, which states that if we multiply any matrix with a vector, all we get is the linear combination of the columns of A. Okay. So let's try to understand what this means. And let's see this here. Stop presenting. Okay. And just for a moment, let's have a look here on the board again. And we want to explain what we saw on the slide, okay? What we had over there. So, what the slide was saying that when we multiply a matrix, and what is the dimension of this matrix A? You can write it again. is 2 by 4, right? If we multiply this one with a vector, what should be the dimension of this vector? Can you tell me? First of all, it should be a vector which has 4 rows, right? So this is the only possibility to multiply matrix A with another vector, because this vector A, matrix A, it has 4 columns, and the next vector that comes to multiply the first one, it should have 4 rows. Are we okay here? So at this stage, then we can, let's assume here we have 2, 3, minus 1, 4.
Professor, can I ask something?
Yes, sure.
So this means that the vector should be four-dimensional.
No, it's one dimension, but it has 4 rows, okay? A
No,
vector,
I'm talking about the vector.
yeah, we don't simply say that it is 4-dimensional, but we say that the vector has 4 rows, okay?
Okay.
So yeah, it looks like equivalent, but it's not that equivalent. But thank you for the comment. But it looks like if matrix A is 2 by 4, we multiply the vectors which can be only 4 by 1. And now what we saw on the PowerPoint slide, it was saying that multiplying a matrix with a vector, what it really is going to produce a linear combination of the columns. Okay, what are the columns of A? Let's write here for a moment. What are the columns of A, of matrix A? The first column is what? Can you read the first column for me? This is the first column, okay? The second column, it is 3, 5. The third column, colonna 3. Which is colonna 3? Minus 4, minus 1, and the last column, it is 0, 6. So, then, what we are really doing is that let's multiply these with what we learned previously. First of all, if we multiply a matrix which is 2 by 4 with 4 by 1, what should be the dimension of the result?
2 by 1.
Exactly. So it should be 2 by 1 because these indices are the same, and 2 by 1, that means that we have 2 rows, okay, and 1 column. So we get something like this, 2 by 1. Okay, so what is the first element here? We multiply the first row of this one with this whole column. So we get 1 times 2, 2 plus 9, 11, plus 4, 15. Okay, I think we got 15 here. Okay. The next element, we multiply this row in blue with this column. So we pair them one-to-one correspondence. This 2 with this 2, okay? So this 2 with this makes it 4. 4 plus 15 is 19, plus 1, 20, plus 24, 44. Okay? Okay, we got here 44. Now, this multiplication, what we did right now, this is in fact linear combination of these columns. These are the 4 columns we have, right? So let's multiply here, this is times 2, here we multiply by 3, here we multiply by minus 1, and here we multiply by 4, okay? So a linear combination of these is in fact, let's check what this is equal to. This is 2 plus 9, it's 11, plus 4, 15. Similarly, we get 4 plus 15, 19, 20, 24, 44. Okay? So this is what we were really saying in the previous slide. So saying that matrix times a vector is equal to the linear combination of the columns with these coefficients. Okay? So these two are equal to each other. Now, taking note of this one, because we are going to need this when we discuss about the spaces of a matrix. Okay, so we're going to mention this one. So the linear combination of the columns, it corresponds to one space of a matrix, and the linear combination of the rows of the matrix, it corresponds to different strings. So we're just, for the first week, it's not that difficult, but it's something which you're going to see this one in a more structured way. Okay? So this is, let's pass here. Okay, so this is what, so we said the column matrix of A, we have these lows, associated lows and distributive lows. The associated lows of addition on the top, the first one, it's relatively intuitive, which states that the summation of two matrices adding a third is equal to the first one adding the second two. And that lambda from the second identity, it's a constant, so it's just a constant number times AB is equal to lambda A times B, and that's equal to A times lambda B. Now we can read also the other distributive laws. Some of those are both intuitive, and they are also valid for numbers, not only matrices. Now, we have defined zero matrix, we know what it is, we covered this one a couple of more times. Then we have the identity matrix as shown here. We can define an inverse matrix. An inverse matrix is a matrix which, when multiplied with the inverse of itself, it gives the identity matrix. Okay, that's what an inverse is. And let's see. And the inverse matrix is a unique matrix, which means that a matrix A, it cannot have two inverses. Okay, so any matrix A, it has only one inverse. Here we have some properties. So the inverse of the matrix is the matrix itself. And then we can also see how the product of two matrices, the inverse of that, is equal to the inverse of the second one times the inverse of the first one. Now, here we can get this result because we have this important property. Let me see. Do you see this third? I think you do see. The third property here in this slide, can you have a look at it? So that means that when we multiply several matrices together, we can multiply whichever order we want. Okay? We don't change the places. We don't do BC is equal to CD. We just multiply B times C before multiplying A with B. Okay? So just for a second, you can even write it down. Sometimes writing things down, it helps you understand them better. So if you look at the third identity here, you can immediately apply this third identity here at the right side of the slide. Okay? So look at this. AB times B inverse A inverse, it is equivalent to multiplying first the B with B inverse, and which gives an identity matrix. And then we are left with A times A inverse, and that produces another identity matrix. Now, we're going to cover a couple of examples, but before we go any further, we can also define the transpose of a matrix. The transpose of a matrix is the, let me see actually what we have more. So I'm going to show an example on the board regarding this, but let's see, this was about the transpose trace. Trace is also a very important parameter. Trace is a summation of the diagonal elements of a matrix. If the matrix is not square, we don't have a trace. Okay? Let me see what else we have. I'll come back to the information covered in the previous two slides when I switch to the board. Okay? Trace is it has an interesting property because it is invariant under cyclic permutations of the multiplication of matrices. Inverse, 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 symmetric. Okay. The product definition of rules. Okay. Okay. I think I'll stop somewhere here, but we'll continue with a couple of exercises. Presenting. Okay, so let's have a look here. Back again. So the first thing that we saw a few things, but the first thing we notice, we learn the transpose. Okay, what is the transpose? Transpose, it is defined as Aij transpose of this is equal to Ji. Okay, this is what this means, and this means that the rows of a matrix becomes columns. Okay, so we take the symmetric with respect to some diagonal direction. Imagine for a moment, for this matrix A, we assume that we have like a diagonal here, and we take the mirror reflection. Well, these will not change 1 and 5, but what will change is that, what did we say? We say that the rows become columns, which means that A transpose is going to be equal to 1, 3 minus 4, 0, 1, 3 minus 4, 0, and the other one is 2, 5 minus 1, 6. A, it was 2 by 4, now it is 4 by 2, okay? And this is the transpose of the previous one. Now, that's one thing about these. Then, let me ask you, let me give also another matrix D, and matrix D, it's 1 minus 1, 2, 3. We can ask the following: what is the trace of D? Trace of D, it was defined in the slides, it was equal to D11, okay, plus D22. So the summation of the diagonal terms, it defines the trace. So let's have a look here. What is this here? 1 plus 3 is equal to 4. Very good. We found it. Now, the next question is, what is the trace of A? Let's write here. Can you answer this? What is the trace of A? You can give some options,
A doesn't have a trace because it's not a square matrix.
That's correct. So this is not defined, or it's not defined. To have a trace, it should be square. You are right. A is not square, so this is not defined. Okay, so this was important to go over. Now, another thing that we saw in the slides, it was the inverse matrices. Okay, so two matrices, if we multiply them with each other, and if we get the identity matrix, then they are inverses of each other. Okay, and let's see a couple of examples. Okay. Okay, so here we have a matrix A, and here we have another matrix B, which is equal to minus 2, 1, 1.5, and minus 0.5. So let's multiply these two matrices and let's find what we get. Okay, so here we have these two. If you multiply those, what do we find? Let's write here. A multiplied by B, we get what? We know that when we multiply something, we multiply the first row, okay, with the first column. So this is how we always multiply. And we are going to get this element here. And by the way, A is 2 by 2, B is 2 by 2. What should be the dimension of the product of these two matrices?
2 by 2.
Exactly, correct. So what is this element? How do we find this element? It's going to be this line in blue with this line in blue. So we get 1 times minus 2, this is minus 2, right? Plus 2 times 1.5, this is plus 3. Would you agree? Okay, then let's find this other element here. We multiply the second row, so we draw these numbers in blue, following the blue arrow. We multiply with these elements here, so we get 3 times minus 2. We have minus 6 plus 6. Okay, we found the other element. And now, let's move on here. We multiply this line in blue arrow, so let me take this out for a second. So to find this element, we multiply these two with these two. We have 1 minus 1. And then we are left with the final element, which is going to be here 3 minus 2. So what this is equal to? This is equal to 1, 0, 0, 1. What is this? This is I 2 by 2. So this is the identity matrix, 2 by 2 identity matrix, which means that B is equal to the inverse of A. So here we can say that B is equal to A inverse because A times B, it was equal to identity matrix. Or we can also write the following. A times A inverse is equal to identity matrix 2 by 2 or 1, 0, 0, 1. Okay? So we are good here. And then there is like a rule, so we can come out with it, which states that the inverse of any matrix A, which is A, B, C, D. So let's imagine for a moment, A is equal to A, B, C, D. The inverse, it is going to be equal to 1 over AD minus BC, okay, times the A and D, they change places. So D comes here, A comes here. So these two, they just switch, and we put a minus sign at the B and the minus sign at the C, okay? So this is like a rule, sorry, this is A inverse. Now, can you come up with some numbers? Tell me 4 numbers to test this one. So let's assume matrix A is equal to what? Can you give me 4 numbers?
1,
Yes.
3,
Yes.
10, and 5.
And 5. Okay, that's good. 1, 3, 10, and 5. So this is the matrix A. And let's try to identify an inverse matrix, which in this case, it has to be A inverse. This is equal to 1 divided by what? This
5,
is 5
minus,
yes. Minus
30.
minus 30, that's correct?
Yes.
And here, what did we say? We switch these two numbers, right? We put here 5 and 1. That's the first thing we do.
5, and then minus 3 and minus 10.
Yes, that's correct. Minus 10. And this then is going to be equal to, let me pick up an eraser here. So then this is 1 over minus 25, okay? This is 1 over minus 1 over 25. Or you can write this one better, minus 4 over 100. And well, let's keep it like this for a moment, and then let's rewrite this one. This is 5 minus 3 minus 10, 1. Now, in the slides, we learned that we can define the multiplication of a matrix with a constant. Okay, this is a constant, but this one minus 1 over 25. So the first thing that we can do is the following. We can equal this to, we can say 1 over 25, and we can take the minus sign inside. So this is minus 5, 3, 10, and minus 1. It's the same thing, okay? Similarly, this A inverse, we can write this one also, like, instead of 1 over 25, we can write this 4 over 100. And this 4 over 100, this is going to be minus 5, 3, minus 5, 3, 10 minus 1, okay. And this is equal, let's divide by 100, so we have this 4 times divided by 100, this is minus 0.05. This is 0.03. Here we get 0.1, and this is minus 0.01. Okay? Then, still, the multiplication of this matrix here, which is 2 by 2, by a constant, it still works. It is defined. So here we get something like 4 times 0.05. This is minus 0.2. This is 0.12. Here we get 0.4, and this is minus 0.04. Okay? So here we found out the inverse of this matrix A. So if we multiply this A with this matrix here, we should get a 2 by 2 identity matrix. Can we simplify this a little further? Probably we can. It looks to me that we can factor out 2, but we can leave it like this. We can always move in and out constants. But it looks like this here, this is the A inverse of this one here. Is it clear? We can test this one. We can check if we did everything correctly. It should be correct. So this is, I'm going to say the definition of inverse of a specific matrix. When matrix is large, it is a little difficult to correctly find it. It is findable, of course. It is well defined as a function or as an inverse matrix. But there is a problem. The inverse, it does not always exist. Okay? Not all the matrices have an inverse, or inverse is not always defined. When the matrix inverse is not defined, we call the matrix singular. Now, from what you see here on the board, can you figure out when the inverse of the matrix is not defined? It is written on the board. You have to find it out. Okay. For what?
Maybe
Yes.
when AD minus BC equals 0.
Where are you looking at? Say it again.
At A minus.
Mm-hmm.
So AD minus BC, if it is 0, then I think it is not possible.
That's correct. You're right. You are right, sir. When this parameter, when this is equal to 0, then that means that the matrix A does not have an inverse, which means that when you gave me these numbers 1, 3, 10, 5, that means that how can I play these numbers around? We can let me see. This could be, for example, 3, 5, and this could be 2, 6. Okay? If this was the matrix that you gave to me, the inverse of this matrix is not defined. So this would be a problematic. Because 6 minus 6 would be 0, and then this would not be defined. You are right. So it was obvious. This was like a formula. How we can use this one for simple case of 2 by 2 matrices. And at the same time, we were able to determine a negative condition which prohibits a matrix of having an inverse or making the matrix a singular one. So let's write this here. So this matrix here, this is singular matrix. Okay. Okay, so any question, anything that is not clear? You can ask me, of course, also later by emailing if you have any problem. Most of our communication, it will be on Google Classroom. That's the platform we selected now. And